today. This is modeled after a 1975 IMO competition problem. And essentially, we're dealing with the sum of the digits, and it's nested in a manner of speaking 3 deep. So it took me a little while to wrap my brain around this thing. But we have this huge number, 74 to the 77th, and we've assigned the sum of the digits are related to x and y. The sum of the digits of y, we're supposed to find the sum of the digits of y. Okay, but x is the sum of the digits of 74 raised to the 77th power, and then y is the sum of the digits of x. And we're supposed to find the sum of the digits of y. So you see it's nested 3 deep. Now we are dealing with decimal digits right here. And so the very first part of this is about bounding the digits. And we wrote down something that's pretty obvious here. 74 to the 77th is less than 100 to the 77th. And we chose 100 because it's easy to count the digits. 100 raised to the 154th, which is 10 squared raised to the 77th, if you're wondering about the rules there, has 155 digits. The best way to see that is just think of 10 to the third power. 10 to the third power is 1,000. That has 4 digits. So it's always one more digit. It turns out to be not that important. But anyway, we do know that 74 to the 77th has less than 155 digits. Now, we multiply by 9 down here to get an upper bound on the sum of the digits because the maximum decimal digit is 9. So that explains the presence of this 9 right here. Now, this statement right here takes a little time to process. Now, notice right here, folks, right here when I say the sum of the digits of x, the sum of the digits of x, that is just the same thing as y, okay? And I could have written y down there. I thought maybe it would make it more readable to actually say it. But this, as you can see up here, that's how y is the sum of the digits of x, right? And so that is y, but I just, hopefully that made it more readable to write it that way. Now it's at a maximum when x is equal to 999. Notice that the sum of the digits here would just be 18. 9 plus 5 plus 3 plus 1, the sum of the digits would just be 18. Okay, I'm writing it right above there, folks, 18. The sum of the digits of this number, 1 plus 3 plus 9 plus 5, is 18. Okay, now it's interesting that a smaller number has a larger sum of the digits. The sum of the digits here is 9 plus 9 plus 9, which is 27, right? Okay, and so that's why we could write this down right here. All right, we could write down the y, which is the sum of the digits of x, is less than or equal to 27. Okay, now the sum of the digits of y is actually has to be less than or equal to 10. And if you look at that, 7 plus 2 is 9, but 19, let me just write it right here. 19 is less than 27, right? 19 is less than 27, but 19 has a sum of the digits equal to 10. Okay, so it's similar reasoning, you know, to what we did above, where 999 was an important number. 999 was the important number for maximization. Here, 19 maximizes the sum of the digits of y. Okay, so and 9 plus 1 certainly adds up to 10. Okay, now we're in pretty good shape because we know that y is less than or equal to 10. The answer to this problem is a number less than or equal to 10. And right here, I'm going to use the truth that you can kind of cast out the 9s here. We won't go through the proof of this, but it's basically because 10 raised to the n is always congruent to 1. And of course, that is mod 9. It's real easy to say. For n equals 1, you get 9. For n equals 2, you get 10 squared, which is 100. 100 minus 1 is 99 divisible by 9, right? Okay. Now, the rest of this is more or less laws of exponents and using one more result that you may or may not be familiar with. There's a result. It's Euler's well-known totient function. They call it totient or the phi function. And it looks like this. It's this symbol phi with a little slash through here like that. Okay. Now, the standard result here is that if A and n are relatively prime, a to the phi of n is congruent to 1 mod n. Okay, now here our n is certainly 9. Okay, our n is certainly 9 in this case. So the n is equal to 9. Obviously here, that's what this result right here depended on over here. Now, so what we can do is note that the totient function is the number of integers less than or equal to n and greater than or equal to 1 that are relatively prime to n. Now you can do that. There's formulas for it, or you can just go through it and see it's everything except the multiples of 3. But b of 9 is equal to 6. And that means there's 6 numbers less than or equal to 9, greater than or equal to 1 that are relatively prime to 9. Okay. And that's based on, this all works based on the order of a number. You know, it works out fairly nicely. But in any case right here, that's what happened right here. That means that 2, right, let me just write it directly above. That means 2 is 2 raised to the 6th is congruent to 1. Oh, sorry, that's a 2 raised to the 6th power. 2 raised to the 6th power is congruent to 1. So you see how this 2 to the 6th just simply got replaced by 1, and then 1 to the 12th is just 1. And 2 to the 5th is what? 32. 32 minus 5 is 27. So we get 5 is our solution, folks. 5. Thought it was kind of cool. And so I'll just write the answer. The sum of the digits of y is 5. That just shows you this huge number, after you compress it down by taking the sum of the digits 3 times, just melts into a single digit number. Thought that was pretty fun, folks. Hope you did too.